and present some of the upcoming work. So I'll try to be more introductory and maybe motivational rather than just spelling out the conclusions of the upcoming paper, but I should maybe write down the title of the project and my collaborators, which we so yeah, vaguely I'll be speaking about the paper. Supersymmetry. And this is done with wire. And then comes right, but yeah, I don't have any particular agenda, so I can spend more time on motivation or just move towards the actual goal, or so just stop me or tell me if I'm going too slow or too fast. So that's for the introduction. But yeah, okay. So the idea of the project is to marry these two generalizations of string sigma model. So when we naively study string theory, right, we start, at least from the worldsheet perspective, with this sigma model where we have we study maps of the string worldsheet into some target space. And now we can do various generalizations or various via exemplifying some symmetries of the model. We can embed them into the picture. And, two of these generalizations I have in mind is introducing supersymmetry in the manifest way via superspace methods, and the second thing is making the model T-duality, manifestly T-dual. So, and these two generalizations have to do with replacement of the source and the target via some extended manifolds. So, in the, for starters, this is just two-dimensional bosonic worldsheet, right? That's just something, if you're just describing a non-interacting string, it will be just maybe a cylinder, right, with the coordinate tau and sigma. And the nicest way to introduce some supersymmetry is making this into superspace or super Riemann surface. And there's so we will replace this one by to super Riemann surface, meaning that we will not only have the tau and sigma coordinates, but also some two fermionic coordinates on top of the two bosonic guys. So I chose to use these light cone coordinates plus and minus, and to make it a bit more systematic, I can also do the same for bosonic guys. So sometimes I will interchangeably, I will use either tau and sigma or x plus and x minus. And what I mean by x plus x minus, I mean the light cone coordinates here. So sometimes it will be useful to use these guys instead. Okay. So this would be 1.1 superspace or 1.1 RNS description of the sigma model. We'll go a little bit further. Some models admit 2,2 supersymmetry, so extended supersymmetry on the worldsheet. And that would just amount to extending the fermionic coordinates to not 2 of them, but 4 of them instead. So then there will be some extra extension to come to superspace later on. And this one, okay, so this is all well known and studied, and there's nice theory and interesting geometry appearing in the target space. It will become more challenging if we try to do it at the same time with the extension of the target space. So what kind of extension of the target space I have in mind? It's some extension of the, so if, again, forgetting about the supersymmetry part of the story now, we can just extend the target space to a double space. So instead of having this M, which has maybe coordinates x1, x2, x3, we can actually have target space where we have double the amount of coordinates. And with each x, there would be its pair x tilde I. And why on earth would we do this? It's because there is this interesting symmetry in string theory, unlike in the world line models, and that's the T-duality. And if in the same way as with the idea of superspace, here this was all introduced to geometrize some hidden symmetry, the supersymmetry in the supersymmetric models. This is really to exemplify and geometrize the T-duality symmetry of the string models. So these are these two secret symmetries of string theory, which you can make more geometric via extending the target or source. And the natural question is, can you do this together? And if yes, like what is the model describing the dynamics of the string? So maybe okay. I will first talk about maybe a little bit of motivation how these models come about, and maybe remind you a little bit of T-duality, and then I don't know if I have to say much in this room about superspace. Probably not. Probably everyone knows that, right? Or not really. I'll remind some basics, but well, you can tell me when we get there. But yeah, first this side of the equation. So is this okay? Maybe are there any questions at this point? No, probably not, right? Okay. So T-duality. So this is some interesting symmetry of our models, and it's not really symmetry per se, because it's a duality between two sigma models, right? In the simplest situation we can have, if we have a source with the target being some S1 times n, meaning that there's some distinguished circle in our target space manifold. There's a way to write a dual model under some restrictions, which I'll talk about in a bit. There are isometries on S1. So under some restrictions like that, we can write a dual model with a different geometry like this. What I mean here is that this will be on radius r, and the new circle will be of radius 1 over r. So this is a different target space for the sigma model. Yet if you look at the spectrum of both of them, they share the same spectrum. And there's just some changes in which one numbers count what, and so how does that work? So if I just single out this S1, right, I'll forget about the rest of the target space. I can look at my embedding coordinate. Where from Slender. This one. And having this extra, so you know, if normally there would be a momentum and the oscillating modes, right? There would be the usual thing in the non-compact target, right? So we would have these oscillators and momentum of the center of mass of the string, right? But if we have a compact target space or some compact direction in the target space, we also get the winding, and winding is really telling us that if we undergo a monodromy, meaning that we go around in fixed time, we go around the string. Where do we end up to some addition of the revolutions around the circle? So this is a new quantum number. That's the maybe the R also. Right, this is a new quantum number. It tells you how many times the string revolves around the circle. So in given time, going around the sigma circle here amounts to maybe going several times around the circle and the target, and this omega counts the number of revolutions. And in a similar way as so now by the logic we know from particle physics, if we have this P, there would be there's a x associated to it by a Fourier transform. And so now if you have this omega, you should also have some dual coordinate to that, right? You should have a Fourier transform for this guy. So there should be some x dual coordinate corresponding to this quantum number, and that's where the idea of having some double target is coming from. That you have these x's and x duals coming together, and they get somehow switched. So how does this work with those isometries I was talking about? So if I start with again with with something very familiar, so this would be my defining Lagrangian, right? For some target space manifold with metric geometry and B field B, maybe. And now I can, provided there are isometries. So this is the simplest setup I can have. There's other less restrictive situations, but I only have a T-duality here. So provided I have a isometry, meaning that there's a killing vector in the target. So this is a point vector in the target. Along which the G and B is constant. I learned that so if this is true, it turns out that this model has a rigid symmetry. It has a shift symmetry in accommodated coordinate to that direction of the killing vector. Okay? So if I choose this killing vector to be along one of the directions, or well, in other words, I will choose the coordinates such that this B is a coordinate vector field. This will basically mean that my G doesn't depend on that particular X, right? So there will be no dependence. No dependence on X. That's one of those, which is the isometric direction. And the only way they will enter the Lagrangian is via these derivatives, right? Not as a functional dependence in G and B, right? So then clearly maybe I will single out one of those. This term.
Is it enough that the lead derivative of the sum vanish?
Second.
Is it enough that the lead derivative of the sum?
I don't think there would be much much coming out of that if because they are in different reps, right? I don't think you would get something less restrictive by considering just some. Or do I? No, I don't think so. Okay.
And okay, another stupid question. If I really will insist of the new radius, T-dual radius 1/r to be a dimension of length, should I then put in the string scale squared?
Oh yeah, sorry. There will be I mean, it would be like because dualized.
Oh.
Yeah. Sorry. Yeah. There's some lines involved. Yeah, that is going to make sense. Sorry. Yeah. Right. So if so let's choose that I to be 0 for now, the isometric direction, and then split out that Lagrangian into the isometric part and the rest. Right? Here. By these i's, I mean everything else than 0. And now, okay, so each of these entries of the original G and B field, they don't depend on X0 explicitly. So clearly, if I shift X, so if I perform this rigid symmetry, X0 goes to alpha, right? So I take my X0 and add to it some constant alpha shift. It will all be killed by the derivatives, right? So that's a symmetry of my Lagrangian. Okay? So every time I have killing vector in the target, it yields some rigid symmetry in the model. Okay.
Should be 4 terms, right?
Second.
Should be one more term, right? It should be a xi, x0.
Oh yeah. Oh yeah. Thank you. Right. Well, right. Right. And now, so the way to perform this this switch from this model to this model is by arranging this symmetry. So we can do that now.
Can I have a quick question?
Sure.
Are these like equivalent descriptions of the same thing, or if you have like one direction that is circular, does that imply that you have a scaling vector automatic, or is these like two different
No, I mean,
cases, or is it just,
I mean, just the fact that in the target I have some compact cycle, that doesn't mean that there's a kind of vector in the model. There's still, I can still have any kind of metric on the target space manifold, right? That's an extra restriction on the model, right? So there are other types of T-dual like symmetries, if you know, with some less restrictive requirements, because this is rather harsh, right? It's telling me that the metric is constant along that cycle, but I can relax that a little bit and still have some kind of like these possibly dualities, but yeah, I'm not thinking about that right now. But yeah, I mean, it's definitely very restrictive and an extra requirement of the target space geometry. Right. Okay. What was I gonna? Oh yeah, the gauging. Right. So now to go from one model to the other, I can gauge this symmetry. What I mean by that is that I uplift this rigid shift alpha into a function. Right. So clearly, if I make it a function, it will cease to be a symmetry of the Lagrangian, because those derivatives will not kill it. So I need to do something about that. And if I want to maintain that as a symmetry of my model, and the way to go about that is, you know, the usual thing we do in minimal gauging, like when we uplift the E1 rigid face rotation into a local one. So we introduce some gauge fields in the game. And when we do, how do I do that? So now I basically, maybe I don't have to rewrite the whole Lagrangian, but basically every time disappears in the Lagrangian, right? So minimal gauging. Gauging takes all of these objects and all of these objects and makes them into this invariant combination. It replaced this like that, right? So it might not look like the usual gauging, right? Because with the usual gauging, you would have a zero component with x, but it's because this is a shift translation rather than some sort of rotational reaction of a like a linear action on the exponents. So, but it's the same idea. And now if I make x's to transform with this function, so no function, alpha function, then I better make my alpha the a0 to transform accordingly as a minus plus minus on that, right? And this way everything will cancel out and we still have a symmetry in our Lagrangian. Okay, and but now we change the field content of our Lagrangian, right? We have a new field A. We can add an extra term here. So eventually, okay, so I'll first write it and then I'll explain why it's a good idea to do such a thing. So I can take the original Lagrangian, maybe well, 0. Do gauging, meaning that I uplift to the local symmetry and I introduce these gauge fields, right? So instead of having all this dependence on x, I now have a maybe gauge x0, x5. and I add extra term. Is this clear? This is the Lagrange, right? It's the same one where I.
There's a small difference between A and A0, so you also introduce A to the other direction.
No, I only have a, sorry, yeah, I only have a not here, sorry. Okay, and right, and but I'll add extra stuff here. I will add this x naught as a Lagrange multiplier, which will enforce flatness of this gauge field. So. Of the gauge field. Why would I do that? The reason is that now I have this mu Lagrangian, this whole thing, I'll call it parent, and it has this sort of hierarchy with the original Lagrangian in the following sense. So I have the parent, which depends on x naught dual, xi, and a naught dual. Sorry, a naught. Now, if I integrate out x tilde naught, meaning that I vary with respect to x tilde naught, and I vary and I solve for those equations of motion, and I feed them back into the Lagrangian, I will get some effective model where I integrate over one of the fields. What happens here, right, is that since this is just linear and sort of entering in a auxiliary way, there's no differential equation for it, but it enforces that flatness, right? That's how I introduced it in the first place. And so locally, I know that if this is flat, I can write this as a function of, sorry, as a d of some function, right? And I can feed that into this Lagrangian, right? If I feed it here, this goes here. If I plug it back here, the only way where it entered was in these covariantized derivatives. So this will get I'll just explain for the plus direction. This and same for this guy, and I can just field redefine my x naught to x naught plus f, and when I do that, I will end up with the original version, right? So I'll end up with the original geometry. So I did nothing, right? I have this equivalence on integrating on x naught, but now you can. I suggestively wrote it as x naught tilde, right? So that there's some relation to x naught. And I can do the other way around. I can integrate over x0. Right? If I do that, turns out that so if I integrate x0, I can do the same thing with the varying with respect to x0 and plugging the equations of motions back into the Lagrangian, and I'll end up with Lagrangian, which will now have no dependence on x naught, but the dependence on x tilde will survive. And no dependence on any. Right. And this dual Lagrangian, so now we have these two ways to like sort of choose which is our physical coordinate and which thing is being integrated out. And actually I can even go further and I can choose some other linear combination of x tilde and x naught to be integrated out, and the orthogonal combination would survive as an coordinate. So there's this whole rotation of choices of what is physical and what is not. And what's interesting is that if you now identify, so this original thing depended, had as extra parameters this G and B, right? And if you pull it up, the G and B remains in the Lagrangian, and if you integrate out the dual coordinate, it will depend. Well, it will still depend on G and B, right? But it gets repackaged into a new set of G and B's, which are connected to the original ones, and they are connected by the famous Busher rules. And so they now describe a new target space geometry. And interestingly enough, since we originally wanted this to be a conformal model, these two had to satisfy super private equations of motion, and if we do this pulling up and pushing down to the dual model, these G tilde and B tilde will also satisfy super private equations of motion. And so that's despite being very non-linearly related to the G and B, right? So that's the usual story. But it's very, we will want sort of, as a starting point, this is not as great. You will want something maybe more democratic, not starting from a particular chosen physical section like this and uplifting first to the parent model. You would maybe want some overarching Lagrangian to begin with physical and dual coordinates, and then choosing a physical section to start with and ending up with one of the dual descriptions. And that's what I'm going to talk about next. And there will be a Hall's double model. So this was a big motivation for Hall's model. Is there any question at this point? So now the idea, it's not very straightforward to guess how the model should look like from these considerations, but somehow maybe for proceeding, if there are more isometry directions, right? This was just one isometry direction. If we now generalize to target space being torus times something else, so we can shift to the slight generalization into torus times space, right? Rather than just S1, we can have more S1s here, n of them. And then if this will be the case, we'll have more isometries along each of the cycles of torus, and each of them will, we can align the coordinates with the isometries, and each of them will acquire this extra dual coordinate in the model. So this is just a usual tutorial model with n isometrics. And so now I kind of want to write a model where I have these, where I'll have xi's. So what I'll do is that I will describe these as xi's, and the remaining ones I will call y alphas. Okay, take it upstairs. And then I will double just these isometric directions to a doublet for each of the isometric directions. And the model which we'll describe will be the following. So first to note this by double x. And now I can write a model which will there will be extra stuff. I don't really care about it, but I'll write it down. And the last term will be just last term. I won't even spell it. It will be something in the base, right? So there's no restrictions on the base part of the Lagrangian. It's similar like here, right? It's the similar splitting as we considered in the one isometric case. So I have some fiber directions. I have some mixed stuff, and then the base, right? So I did the same thing here. I have purely toroidal part. Then the mixed stuff and the base, and the only and the doubling happens in the fiber directions only. So if I forgot about the X tilde here, I would just have the similar splitting. But I do the splitting and then I double everything into fiber, right? And furthermore, so this is something I'll check. I'll tell you what it is. Next, I had a hard time getting that correctly. Okay. So this H is something constructed out of G and B, right? And the way they enter. Okay, so I'll write it in the. Maybe I'll write it upstairs. Okay, so this H. It's this kind of object. It's a 2n. So if my fiber directions part was n-dimensional, this is 2n by 2n matrix. It naturally acts on a space which is no, that's annoying. I have Tn, but it acts on this space very naturally. So on the sum of the tangent and dual space. So this is 2n, right? 2n by 2n. You can see that you know, if there was no B, right, I would just have this middle guy. So naturally that's on a vector and a form. That's why it's on this space, right? That's why this inverse is up in this right upper corner and G is in the left bottom corner, right? Because G is vectors and creates forms, and G inverse is forms and create vectors, right? That's what metric does. Right, and So we call this thing generalized metric. It's sort of a right analog of a metric in the double space, in the space where x and x tilde provide us with the coordinate description. And there's some properties coming along with it. One of them, which will be important in the model, is that it squares to 1. For each choice of G and B, it squares to 1. That's quite interesting property. But since that's true, it allows us to define these projectors. So it allows us to define these two projectors. Like that. Maybe I was a little unclear here. So I'm talking about H with one index upstairs and one index downstairs, and here I have H and B with two indices, both of them downstairs. And the way I lower and raise the index is via this metric, A, which is as follows. So maybe someone knows H more of just in the form of it with both indices downstairs. And okay, so that's that. Now I can define these projectors, right? Because it squares to 1, so I can have this, and using that I can support my my Lagrangian with constraints. This is not the full story. We need extra constraints to accompany the Lagrangian to actually describe something physical. And the constraints are the following. It's so these are the constraints. You can write them in various other ways, but you can feed in this expression, right, and maybe write it in a different way, like separating the stage dependence on one side and identity on the other side, if you see that. But the thing is that it allows you to what's important about these, they are sort of like self-duality equations. By that I mean, if you study two-dimensional scalar field, right? You can have these kind of equations, maybe. Right? This would be your self-dual boson, and this is kind of a extension of that, in a sense that if I have more scalar fields like this, and I have this star operator which squares to 1, there's an easy extension of these kind of self-dual constraints by adding some endomorphism acting on the space of fields, which also squares to 1, right? Then I also get some viable boundary some viable self-duality conditions, and that's exactly what we have here. And what it allows us to do is to express either x's in terms of x tildes or vice versa, or some combination of x's and x tildes in terms of the orthogonal one. And upon plugging it back into that model, we end up with either the original physical model or the dual model, or something in between, perhaps, based on how we choose to solve these constraints.
And you want an index A on one side and B on the other side?
You mean if I spell.
No, not that, the next one.
Oh, yeah, sure, sorry, yeah, sorry. Yeah, so this, right. I'm gonna do something like this. Okay, so this is Hall's double model. It's a replacement of the parent action without need for the annoying extra gauge field, and it sort of encompasses all the possible dual pictures of the model. So.
X still in zero solution to us.
So again, sorry.
Setting X tilde to zero a solution to the constraints.
Yes, right. Well, not really. No. It's that I can write X tilde in terms of X's. That would be solving for the constraints, right? It's not that I set them to zero. And now, okay, the question we basically asked ourselves in the paper was talking about in the beginning is that can we write some supersymmetrized version of this for I guess various reasons, mostly out of curiosity. Can we supersymmetrize this and make it work with either 1-on-1 superspace in the source or even 2,2, and so yeah, that's what I'm gonna talk about next. And it turns out that so in 2 sentences, so if I don't know how much time will I have to finish everything, in 1-on-1 superspace it's all very simple, and that I'll just cover now in 5 minutes. In 2,2 it's a little more hard and requires some extra constructions. So, and the reason is very simple. So 1-on-1. So maybe a quick recap of 1-on-1 superspace methods, right? So basically, without going into all the motivation why do we need supersymmetry and what it is, I think people know that very well, right? It's just the way to geometrize supersymmetry on the source by introducing these theta plus and minus, and uplifting all those embedding coordinates into superfields. And 1.1 is very minimal, and the way it goes is really that we have these original fields, and we now replace them by superfields. And since these are very many coordinates, we can expand them, right? That's the usual thing we do. And so all this is really just a bookkeeping parameter to introduce some new fields in the data via.
Can I suggest you call this more X for sigma or something? You have so many X's, maybe you want to call them the worldsheet for sigma.
Oh yeah, but then it's like sigma squared. Yeah, that's true. What about if I capitalize like that? Because then like sigmas are no it's here. Sigmas were like part of the X plus minus 1, right? And these like yeah. Sorry. Then we have this expansion, right? Which necessarily terminates because these are fermionic. So we extended our field content from one bosonic field, right, into one bosonic field pair of fermionic fields, because they're standing next to the data plus minus, and one of these important auxiliary fields which enter the model to make the supersymmetry of shell. And now,
So there should be two thetas multiplying.
oh yeah, sorry, that's true. That would have been. And now without going into nitty-gritty details of how you construct stuff, there's this minimal substitution happening in 1.1 Lagrangians. We basically every time I would see my plus or minus, I can replace it by superderivative plus. Right, where these are these guys. Now you see the power of this formalism, because plus sort of comes in a R charge, so you have 1 plus here and 1 plus and 2 plus downstairs. So that's why I know how to write that expression. Okay, so now if I without doubling, if I have a bosonic model, the one I wrote at the beginning, like this. I can just think of these now as superfields and replace these by B plus and this one by B minus. Right. And change the measure in the integration when I define what the action is. So I set this with if people know this, that's something I should comment more on. And so if so this is 1.1 supersymmetrization, right? 1.1 extension. So now if I performed this fermionic integration, I would see that I would get a Lagrangian, bosonic Lagrangian now, which will depend on all these 3 fields, or 4 fields, where these are 2. And if I just zoomed into the part which depends on X, I would get the original bit, and then some extra stuff, which will make it into supersymmetric multiplied, right? But and okay, so this is the 1.1 extension, and I can do very straightforward extension of the whole model. So I don't even have to explain much here because it's really straightforward. I just you can probably all guess by now what will be. I just take the original model. So I take this thing. Sorry. Extra stuff. And by extra stuff, I mean all these cross terms and the base. And so this will be my R. And the constraints. And I just erase all these partials and substitute them with D plus and D minus. Right, so that would be my 1.1 supersymmetrization of polynomial, and everything works. Everything's beautiful, and like the constraints still make sense. So yeah, I'll just do that. And I mean, obviously, this is not Hulík even mentions it in his paper somewhere in the footnote. You know, there's obvious generalization in 1.1 superspace. And this is what it is.
Okay, so I guess the key plus plus and key minus minus doesn't really make sense in the non-SUSY model because it was just the projections.
Oh yeah, it's just, oh yeah, sorry, yeah, okay, that's why did I do that? That's true. Yeah, I don't know why I did that.
Anyway,
Yeah, I guess.
anyway,
Plus everyone,
it's
yeah.
clear.
Yeah. But now, okay, now the 2.2 extension is slightly more involved or surprising maybe. Okay. So now, okay, so at least if I don't make it,
Can you push up?
yeah, sure. So if I won't explain everything due to lack of time, at least now you know what we try to do. We take that whole model and we try to make it 2.2 supersymmetric. And so with 2.2 supersymmetry, it's slightly less straightforward how to, make a 2.2 model out of bosonic one. Because it imposes more restrictions on the target space geometry. So here the thing was that if I had a bosonic model with some target n, I had I had no restrictions on making this into super Riemann surface here. Well, I guess except for M having a spin structure, but that's for physicists, I guess that's not really a restriction. Right. So, but now if I wanna proceed further and I wanna have more supersymmetry here, the target space geometry will be restricted down to something restricted. So what I mean by that is that here I just have the geometry is covered by G and B field here also, but these will be of some special form, and the easiest class of these target space geometries which admit the 2.2 superspace description are killer geometries. And killer geometries, they are killer manifolds. They come equipped with the G, and they are complex. So they have a complex structure which is integrable, and omega that's a killer form, and these three structures interact. So basically, what happens is that this is the omega, right? G is Hermitian with respect to J. So this is true, right? And furthermore, if this J is integrable, I can actually. So this omega needs to be closed, but then furthermore, I'll be able to split D to homomorphic plus antimorphic exterior derivative and use del parallel and finding potential for omega. So omega is due to this G being Hermitian, it's form of 1-to-1 type, right? Meaning that it's something what has Z and dz variations in it, rather than all the two forms So right here, I mean, I would have things expanded in these objects. Here, use that. And out. Right. So omega is only in this part of the expansion. Right. And there's potential coming along with it, which we call color potential. Color potential D. Which is a function of z in the bar, not really a function, but it's defined onto some shifts, and it's such that it provides a potential for this omega, meaning that if I take its Hessian or Hessian, it will give me this plane change form. Right. Okay, so that's the Keller geometry in very quick terms. And now, so having this Keller, so it's very neat repackaging of the geometric data. We don't have the G and B here. We just have this one function B, and that defines for us the omega. It secretly knows about the complex structure, right? It knows what is the z and z bar direction, and by that we can also reconstruct the G, right? So it sort of nicely repackages all the data in one function. And now having this function, so for every Keller manifold we have this function, we can.
Sorry, can I ask?
Yes.
So where is the B in this picture? Does it?
Oh, there's no good question. But there's no B in Keller geometric case. There will be B in more relaxed types of geometries in the target. In general, we can have these generalized Keller geometries in the target, and they admit B field, and there will be something more general than the color potential. I'll probably not get to that, but yeah, there's for that you need extra stuff. Okay. Right. Right. So if having this color potential, I can now write down a model which doesn't look like one-on-one model at all. It will be something written in terms of superfields. Okay, so first, what will be those superfields? They will. So that's something we could have guessed. There will be fields which will depend not only on theta, but also on theta bars. So 4 of them now: theta plus theta minus theta bar plus theta minus bar. And they will be supported. So this is a lot of extra Fermi coordinates, right? If I expand it, I will not only that amount of fields now scales exponentially with the amount of data, right? So I will not only have the bosonic field X and these fermions and the auxiliary fields, but I will have what 16 components in that expansion. So that's a lot of components. I don't know that many, and for that reason, I need to cut it down by some constraints, and those constraints are called chiral constraints, or the chiral. So I will require that D bar kills my X like that. So this is these fields that we call chiral superfields. Right. And now the model itself, it's So it's something very natural once you know about this killer potential in the generating all the geometric data. So you can just construct Lagrangian like that, and to see that it actually gives something sensible, you can do this partial integration of the Fermionic coordinates. So this was the model, right? It had the fields Z and Z bar, which were two-cumulative superfields with these conditions D bar killing it. And now I can perform partial Fermionic.
So
Yes.
so you changed superfields from X to Z, just very good.
That's true. Yeah, and I didn't.
Maybe you should put the X instead.
Maybe I can put Z here because X is where kind of real coordinates. That's okay.
And to the left.
Yeah. Yes. Okay. So now I can perform partial integrating out of the theta coordinates, and the way I would do that is by dividing my thing. So would be this. I can split my Fermionic coordinates into real and imaginary part, and I can integrate out these theta guys, meaning that I hit this Lagrangian with the D plus, and I think this way I will eliminate these two guys and keep just theta 1 plus minus in the picture, and I will reduce from 2.1 to 1.1 superspace. And but I need to remember that while I'm doing this, I'm using these constraints. I can, which allows me to switch between D1 and D2, right? Because it gives me D bar, so D plus minus. So it allows me to exchange all my D2s for D1s. And if I do this, I will end up with some 1.1 model, and I can read off that G or possibly B if there's a B in the model. And it turns out that it will exactly like fit this description what I gave you. There will be two derivatives on the and we will read it right. So if I do this 1.1 fraction, I will end up with what I have this kind. And this G, I should go do derivatives. I found the color potential. So now having knowing about this reduction and basics about two-dimensional superspace, we want to do the same thing for the whole. Namely, we want to find some two-dimensional model with some double potential, which upon 1.1 reduction gives us the generalized symmetric H. And furthermore, so you also remember, or maybe not, that whole model not only had the Lagrangian, but there were also constraints. So we need to find what is the 2,2 uplift of those constraints and what is the double potential in a way. Is this okay? Do you
So I just want to ask quickly. This is not unique, this direction from the 2, 2 to 1, 1, because you chose this Kyle condition and then integrated out the bar.
I mean,
you could do it in principle in different ways, right?
If I know that I want to retain theta ones, then I mean, it's unique. But yeah, I guess I could have said that the theta twos were the ones I want to keep. That's true.
Yeah, but also this constraint, this the Kyle superfield, that's also like the only choice that you want to do, or can you?
No, there's actually other types of constraints. And again, that comes in when I have more general types of geometries in the market. If I have different types of geometries, it turns out that I need other types of fields. I might need twisted Carol fields or even more even stranger fields describing the target space geometry. Yeah. And okay, maybe I'll go comment on that too. Okay, so now yes. So now I'll explain for the Keller case how I construct the doubled 2,2 model. So I start with the set bar here, and I will actually have it in the very special form, which reflects the presence of isometries. So I will not. So this will be a restricted type of models where the dependence on Z and Z bar is just via this combination Z and Z bar. Okay. So that reflects the fact that I mean, Z will be I can expand this form. For some reason we chose this stupid parameterization to confuse people in the paper. The reason, no, it's not entirely stupid. It's because this way V depends on mem Y, and it's customary to use the X for the isometric direction in the literature. So that's why, right? So sorry about that. So then the B just depends on the real part of Z, right? It has no X dependence. So clearly, if I start now constructing these target space geometric data, it will be of that form. If you recall at the very beginning of the talk, that my G and B will not depend on the X direction, right? So those will be those isometric corrections. So that's how it's now reflected in this 2,2 model, that it depends on a very special combination. Right. So once I have this, I can perform Legendre transformation of this function p of y. I can find a dual function, right? This is just a function of y. So whatever function I have, I can find a Legendre dual, meaning that it will be a new function of a variable y tilde, and this y tilde is you know, the usual stuff. This where I write this phi in terms of derivative of v and plug it back in, and then I'll take this Legendre dual of v. And now, so yeah, so that's the recipe. I'll start with my.
I guess, strictly speaking, that's the Legendre would probably have a minus from the v, but you don't want, you insist on cross there, right?
So say again.
I think the Legendre would have a minus in front of the v.
In front of the, oh yeah, true. Oh yeah. Okay. Wait,
Of course, it's just
no, I don't. Yeah, sorry.
it's just convention.
Yeah. I don't have that. Sorry. Yeah, so that's a little different, but okay. That's right. So it's almost Legendre dual. But now having this new BD, I can construct this doubled. I can construct this path B, and usually just sum of these two.
It's a minus, or
Sorry, what?
it's minus in this relation.
Which relation?
Y tilde is equal to minus derivative of v.
Yes.
Right, because I'm using oh yeah. So I can construct this thing, and now it depends on z plus z bar and on the w and w bar combination. Now the okay, so that's some potential. Now on the double space of fields.
Did you say what W is?
Sorry, what?
Did you say what W is?
No, but I will say no. It's a 2,2 superfield, but if this Z was chiral, now this satisfies different constraint, which is something what Standa was alluding towards, and that is the following. So it's a little, so before it was both d bar plus and d bar minus killing Z, right? Now it's a little twisted, and that's why we call it twisted chiral field. So the recipe is that I start with my B and I construct the Legendre dual, then I construct the sum of those two, and that one I call double Taylor potential. Double potential. And if I had the chiral fields describing the original geometry, the stuff entering the dual part of the potential is with chiral fields, right? And now, so now I can write down a concise model into superspace. Which is just this. But that's not enough, right? That's just a Lagrangian, but I need to support it with the constraints, and the constraints turn out to be the following. So that's the non-doubled part of the potential. So it's again H. So in Hall model, right? H came into the dynamics itself, and also in the constraints. Here I have a W defining my my dynamics, my action, and but also it enters into the constraints. And now, so okay, so I claim that this is a double extension of the whole model. How do I see that I have to do that 1-1 reduction? So if I perform the normal reduction, you can almost see immediately that if I did this with D and use the constraints, it will give you something. It will give you something. We will hit it with D. Now I'll introduce new derivative acting on this B, right? So there will be two derivatives. B and then D. And then if you separate real and imaginary part of that, you end up with the same constraints in 1-1 extension of whole model. So these are some constraints which reduce in 1-1 superspace to something what you had before. Because again, like the second derivatives of B, they are linked to G and B possibly if there's a B field.
And is the fat V?
Sorry,
is
what?
fat V?
No, it's not. This is just
Ordinary.
just the ordinary. So, which is actually an important point, because if so this was again like a bottom-up construction, right? I started with a model having just chiral fields, and I constructed this double thing. But I could have, you can imagine that maybe you start with a double description, and this constraint, it requires you to choose a polarization. It requires you to choose that what do you call the physical part of the double potential and the complementary part. So you could have just started with the double potential, which would have been a almost arbitrary function. Well, let's think. It's not arbitrary function of Z and the W. It's a function which is Legendre self-dual, meaning that if I dualize in both, it will be the same function. So it's a special type of function. But then it actually turns out that if I have that requirement, it can be always written in terms of a sum of two parts in infinitely many ways, and each way I can associate a constraint to it and then solve it and feed back in and obtain a original model in one of the dual pictures.
So if you had put a minus there, like Klaus wanted,
Yes.
then the fat V would have been just y tilde y.
Why? That's true. Yeah.
Is that manifestly wrong, or could one do it like that?
Yeah, we tried that, and somehow Yeah, but I wasn't the. I don't know. Yeah, it didn't work. That's why we changed those signs there to really get the dependence on the original B and dual B right into Lagrangian. But yeah, there was originally there was an idea actually that somehow all the dynamics comes just through the constraints, but somehow it doesn't work along the way when you're reducing. Like you don't really get the proper description. I don't know why. It's strange. Also, this reduction doesn't commute with the feeding in the constraints into the picture. So you really have to first reduce to 1.1 and then use the constraints to plug it back in. You cannot just feed it here into the Lagrangian and then reduce to 1.1. You also get a different thing. So there's some strange things which we don't understand. Yeah, that's that. But okay, so maybe I don't know. Maybe I'll show you one example where this actually like now you can ask like why would I bother, right, for the normal models? Like, why would I do such a thing? I mean, the original motivation for us was something that's still lacking in the picture, and that is that maybe these four fields now, when I extend, they have some nice, you know, action of generalized geometry structure on them, because you see that in Hull model, right? In the Hull model, there's this generalized symmetric appearing, and if you know about the generalized geometry, you'd be like, oh, okay, so no, all those fields should, I know, have like everything should have nice interpretation in terms of generalized geometry data. And here, I guess I don't want to go into details of it, but for all these 2,2 geometries, they have also nice generalized geometry description. Right? They can be described in sort of generalized complex structures, and we can hope that this procedure will yield nice field space where the generalized complex structures act upon, and everything will be beautiful. And it's not. It's just something's missing, and we cannot figure out what. But we still, I don't know, have some application of this doubling, which is, I think, kind of interesting or nice. And that is in default models. Yes. Sorry, what? Oh, I see. Okay, thank you. So this whole endeavor was rather disappointing because the original goal is still not fulfilled. But what's at least very nice is that we can make sense of some models which admit 2,2 description, but not quite. And what I mean by that is that okay, right, example here. Okay, so the thing is that if it can happen with T-duality that if I perform T-duality multiple times, so I can have a model which I can have a manifold which admits T-duality on various directions. In particular, in this model, there will be 2 isometric directions, so I can perform T-duality twice, and I can perform it consecutively. So I would obtain maybe first time, and then from 2, there will be T-duality. And it happens that for certain, well, for a lot of generic choices of G and B, if I start with G and B here, after this T-duality is completed, this chain of T-dualities is completed, I obtain some G and B. And so if this was, for instance, if this was if this had a S1 direction in it, clearly these G's and B's, they have to be at least periodic along that S1, right? Otherwise, they wouldn't be defining G and B on the circle. But if I perform this chain of T-dualities, these might no longer be periodic around the circle. So how do you make sense of this? It's not really some natural geometric data, right? And these spaces where this fails are called T-folds, and they've been studied a lot. And probably the right way to look at them is by like seeing this put in the double picture. And so we confirm this if we in the 2,2 picture. So we have a specific example where we have G and B, which make 2,2 description. So there is a generating Kähler potential for it, and we'll write it down here. Okay. So this is a Kähler potential, which now sorry. So if I derive what G is in this case, will turn out to be
it gives a non-degenerate metric.
so what?
It gives a non-degenerate metric.
Yes.
Even though there's only linear dependence on like one.
Why? No, there's quadratic one. Oh, here. Oh, yeah. But they will disappear, right? In this term will like drop out in the in differentiating twice.
Yeah, I was just worried about if the y1, y2 term is enough to fix the y1 also. But
Yeah,
if you say it's okay,
yeah.
then
Yeah, I mean it's obtained by performing Legendre transformation twice, and that's why you obtain this. But it doesn't really affect what the G and B is done in terms of noise. Right. So this then yields the following metric and B field. And the B field.
so B field, now we get the B field. So one of the y's corresponds to twisted.
Yeah, sorry.
So it's not here.
Sure.
It's not here anymore.
No.
This is after dualizing?
This is after dualizing.
So you start with Kähler and then you go.
Yeah, and then I obtain this model. And this model actually has a physical significance. It's a geometry described by this mirrored NS5 ray. So I haven't really but the thing is that since these are not periodic, and likewise the B, if you perform that, so Y are the torus directions, and if you perform a monodromy under that, you end up with a different Taylor potential. So meaning that Taylor potentials, they are not really unique functions, right? They are defined up to shifts by homomorphic and anti-homomorphic functions, but here it's even worse. Like if I just perform a monodromy in one or the other fiber directions, I cannot undo it by shift of a homomorphic or anti-homomorphic function. So it's really non-periodic. So but this is not, I guess, congruent.
Shifts in the, no, I think shifts in Y1 are okay. It's Y2 which is not okay. If you would shift, you would get.
Oh yes, sir. So yeah, this is, but this one is not congruent. Okay. So by that I mean this is this plus 2 pi. That can be undone. Where's the other one?
So why?
For what?
If I take this, I shift Y1 with pi, I just get C plus M Y2 times pi, no Y1. If it would be a Y1 there, then you can't undo it. Then you have changed the geometry. So you have to, that doesn't, the road can be great.
Right. No, but this is correct, right? If I
No.
shift. Okay.
No, it's not. That is not homomorphic.
Yeah.
I mean, look at your V. Just take the V and shift Y1.
Yeah, true. Okay,
Y1 is linear, so you just get.
right. So it's not congruent, basically.
No.
I'm confused. But yeah, so this is not a color transformation, right?
Look at that. Look at your potential. And just shift Y1. So instead of Y1, you write Y1 plus 2 pi.
Yeah, I made a mistake here. Sorry.
Oh, okay. That's what I was asking from the beginning. Okay, that's good.
Sorry.
But then it's not a killer.
Yeah.
So
So
then you change it, even there you change it.
neither of them is right. Because there will be W bar Z terms and convex benefit of that. Okay. So this cannot be undone by transformation.
So actually, if Y2 is twisted parallel, you do have some more possible functions there. So maybe
True, but still,
you have to be a bit more careful.
it cannot be right. So I mean, in general, the transformations I can use are these, right? this is the ambiguity.
Right, so are you sure now that this quadratic here? Maybe,
No.
yeah, maybe you're fine actually. Because y2 is twisted here. Right, because you're gonna get only quadratic terms and they're gonna be like z. I mean, the worst term is the only problematic term is y2, y1, the one when you multiply.
Right.
And then you're gonna get, you know, z times w.
Oh yeah, true.
Z times
true.
w.
Okay.
Z bar.
Yeah. So yeah. Okay. So the original. Sorry. After many mistakes, the original is true. Yeah. This is this can be undone. So it is concrete, but this second one is this is not. And it's even worse if I now dualize the potential. I mean, you can calculate that, right? Because it's a polynomial function, so it's easy to perform the dual. It's easy to write down the dual potential, but then it's even worse. I mean, I don't know if I want to write down the dual potential here. It's pretty ugly, but I can show you later because we're out of time anyway. But the thing is that both
there are several dualities. So
there are several ones. There are several ones. But I mean, like here, I'm going to be dualizing with respect to so if I perform the full duality, so twice T-dualize with respect to x1 and x2 isometric direction, okay? I'll obtain the full Legendre dual, and that potential is you know, will depend on some y1 tilde and y2 tilde.
Right, but I thought you got it by doing two T-dualities. So where did you start to get it?
I mean, yeah, I mean, it doesn't matter where you start, I guess. It's a.
Well, I would be surprised if you start in something which is more ugly and then something which is simpler.
This was so this describes the NS smeared NS5. And
Here because it's T-dual. So if you take the T-dual in the transverse direction, maybe you will get something non-smeared.
I don't really, yeah, I don't know. Like this is something we read off the paper and just took it for granted and noticed that if I have been already here, it's not congruent with the original one upon transformation.
Okay, so you didn't get this by doing starting somewhere else.
No. But I can so now, you know, applying the recipe, I can fully T-dualize and construct the double potential, and then so okay, I can construct this D1 for them, and this thing is even worse. But somehow, if you sum them together, those ugly contributions cancel out, and now you have a general class of, so now you will have this double. And this thing will actually be periodic in the generalized sense, because stuff will cancel out and everything can be subsumed into generalized Keller transformations. So you have actual like geometric description of a original T-float model in this double sense. But every time every time you choose one of the physical frames, you spoil that periodicity of the potential. So it only really makes geometric sense in the double sense and not in either of the physical descriptions. So maybe I'll stop here because I'm taking too much time already. But okay, so yeah, but that's okay. So that I think is a nice thing that we can describe some of the non-geometric models, some of the default models, which are made to come to description. What is still lacking is that we don't understand how to do two things. One thing is that it seems that there is still some need for field redefinition once we perform the doubling of the fields. I mean, it's already kind of nice that you get the reduction to whole model, but to really exemplify the action of those generalized geometric data, you need to do some field redefinitions, and that's not clear to us. Like, we can even read of the complex structures acting on those double fields, but it's nothing clearly related to the generalized complex structures you would have to describe that type of generalized color geometry. So that's something unclear. And the other thing is that it would be nice to be able to, I don't know, perform doubling even beyond the case where you have isometrics, because Hull also has a, so I only describe the doubling here for the isometric directions, but in Hull paper, you can actually go ahead and perform some doubling for non-isometric directions, and then kill it off by the constraints. But it's more democratic. You can then have all the you don't have to do this split into isometric and non-isometric directions. And the problem is here that the supersymmetry actually links the non-isometric directions to isometric directions, right? Because here the isometric directions are along the y axis, and y's are exchanged by supersymmetry. So it sort of breaks the manifest supersymmetric picture, and it would be nice to have just general description for the generic models, which we still don't understand either. So these are like two big questions we cannot really answer at this point. But yeah, okay, I'll stop here. Thanks for attention, and if you have any questions, I'll try to answer that.
Okay.
So please feel free to ask questions or comments. So I'll just start. I wanted to ask about, so you said that you did some restrictions on the background to the 2,2 supersymmetry, and one of the examples was the K-or background. So are there any other examples if you look into something else, or just for the K-or?
Oh yeah, we can basically, so even this model, sorry, I was too fast here, and even this model is no longer Keller. It's a geometry of build type. It's a, so in general, like the most general backgrounds which are going to come up with are these generalized Keller targets or manifolds, which have two complex structures, and those two complex structures, they somehow interact with the metric, and there's huge classification based on whether as to whether those two complex structures commute or not. And build type geometries are the ones where those two complex structures commute. They are not the same. There's one for left movers and right movers supersymmetries. And so this is the simplest generalization of the Keller case. It's the one where the complex structures are not the same in the left and right supersymmetric directions, but they still commute. And based on in which directions they are all the same, and in which if they commute, you can go to accommodated coordinates or complex coordinates with respect to both, and then you'll see that if they commute, that they must be same in part of the space and different by sign, and the place where they agree, that's what is described by chiral fields, and where they differ by sign, that's what's described by the acoustic chiral field. So here already we have to do that, and I just didn't really care to mention that in more detail. And for B field, you need that, like you need at least build. you cannot have B field with just chiral fields or opposite chiral fields.
Okay. So, any other questions? If not, then let's take the speaker once again. We'll be getting here the next week also with check on continuing this stuff.
Should have